Hello everybody, I hope you're doing well, and today I'm going to be talking about the multipole expansion. So just some background that you should probably be familiar with before going further in this video is these electrostatic concepts that I have written down here of force, electric field, and potential. And these are all going to be point charges we're talking about here. So this is basically a table that summarizes electrostatics. So if you have 2 point charges, there's going to be a force between them, and that force is going to be the product of the 2 charges divided by this constant 4 pi epsilon naught times the distance between the charges. Well, the E field is basically a force per unit charge, so you're just going to divide by the force by a charge and you get this E field. And potential is if you try moving a charge through an electric field, how much work you have to do that. That's what the potential signifies, and it's represented by this formula. And force has units of newtons. Electric field has units of newtons per coulomb. Potential has units of newtons times meters over coulomb, or joule per coulomb. Force and electric field are both vectors, whereas potential is not. The potential is just a scalar. At least the potential I'll be talking about in this video. And for the rest of the video, we're going to denote the force with an F, an E field with an E, and the potential with a V, without the vector symbol over it. So, what is a multipole? Well, if you have just one point charge, you can think of it as a monopole. Monopole could just be, for instance, an electron. And the electron, it's going to emit some electric field, and you would draw those field lines pointing in to the point where the electron is. Well, we can also have what's called a dipole. And that's like putting 2 monopoles together with equal and opposite charge. So you can make a dipole by having an electron and a proton. So the proton is going to have field lines pointing outward, and the electron is going to have field lines pointing inward. So you're going to get something like this. And similarly, we can also have things called quadrupoles. And that's like if you take a dipole, say we take the same dipole we got here. We got our electron, our proton, and then let's put a proton here and an electron here. Well, I'm not going to try to draw the field lines, but you can see it's going to look the field lines are going to look more complicated than a dipole. But this is just a collection of 4 point charges, is what you can think of a quadrupole like, or a collection of 2 dipoles. And similarly, we can keep going up and up. We can have octopoles, which would be like putting 2 quadrupoles together, so on and so forth. So that's a qualitative description of what a quadrupole is, or what multipoles are. And I should probably mention that you can also have what is called a pure dipole, which is where you basically have a point charge, but the electric field it emits wraps around itself. There's no such thing as an actual physical dipole. It's mostly just an idea, so I won't really expand on that. And you can have quadrupoles. Now this can be physical, where you have, say instead of this, we have charges that are like there's a proton here, an electron here, and a proton here. Well, there's a dipole here, there's also a dipole here, so this would be a quadrupole. And carbon dioxide is an example of something that's sort of like this. Well, except the charges are opposite from how I wrote them. So now we're going to get more into the mathematical details of multipoles. So, on the previous page I said the potential, which is a function of distance, is equal to the charge divided by some constant times the distance. So that's for a point charge. Now, say if we don't have a point charge, but we have a charge distribution, okay, which I'm symbolizing by this blob here. And let's say our origin is right here. Maybe it's the center of mass. So it's a continuous charge distribution. Well, we're going to have to do some calculus. So we're going to zoom in really far, and we're going to think about just a little piece of charge that has volume d tau. So if we were in 2 dimensions, this would just be the length times the width of the square here. I mean, most of the time you're working in 3 dimensions though, so this is d tau will be a volume. So we will denote a vector from our origin to our charge we're considering, our infinitesimal charge. We'll denote that by r prime. Say that you, the observer, are measuring this charge distribution from way out here at point P. We'll call the distance from the origin to point P, we'll call that little r without a prime. And we're going to complete the triangle here. We're going to call the distance from the charge we're considering to the point P, we're going to call that big R. And we're going to call this angle right here, I drew it where it kind of looks like 90 degrees. It doesn't necessarily have to be, but we're going to call that angle between R and R prime, we're going to call that theta. Now, you can see we have a triangle here. I can redraw it like this, where this would be R prime, this would be R, this would be big R, this would be theta. Now, the law of cosines says that r squared is equal to big R squared is equal to little r squared plus little r prime squared minus 2 times little r prime times cosine theta. That's the law of cosines. It's easily derived by considering, instead of just distances, consider each of these as vectors and take think of big R as the difference between the vectors r prime and r. It's an easy way to derive the law of cosines. You just take the dot product of big R with itself. But I won't do that here. Now I can rewrite this as so all I did here was I took out the r squared and put all that other stuff in parentheses, and then I renamed these two terms epsilon, and then I took the square root of both sides to get big R by itself. Now I can also take the inverse to get So there we go, we have 1 over big R. Now what we're going to do here is something that is done all over the place in science and physics, is that we're going to expand in the Taylor series. So we're going to expand 1 over R will be our function, and we're going to be expanding no, our function is going to be 1 plus epsilon to the negative half. We're going to expand that in a Taylor series. Sometimes this one's called the binomial series, but the more general term is the Taylor series. So just to remind you, what that says is if you have any function of x, well, we're going to do the Maclaurin series, which is a Taylor series centered around 0. This is going to be f at 0 plus f prime 0 times x plus f prime prime 0 times x squared over 2 plus f prime prime prime, well, 0, x cubed over 3 factorial, well, this 2 is also a factorial, plus so on and so forth. You can see each term, the nth term, has an nth derivative in it, evaluated at 0. If we were doing a general Taylor series, you would just replace the 0 with an a, and you'd write, instead of x, you'd write x minus a. So here would be x minus a squared, for instance. But this is general. This is how we're going to do our expansion of 1 plus epsilon to the negative half. So epsilon is our x, and our function is 1 plus epsilon to the negative half. So we will expand that here. Okay, so all I did right there was take the first 3 derivatives of our function, just so it's easy to see that what I'm plugging in for f prime of 0. So our f prime of 0 is these things over here. Okay, so now we've expanded up to 4 terms, 1 plus epsilon to the negative half. So now I'm just going to rewrite 1 over r with this plugged in as 1 plus epsilon to the negative half. Okay, so all I did there was plug in for this thing, and I also simplified the 4th term a little bit there. I divided it all by 3. So I'm going to rewrite this on the next page so we have it for reference. Okay, so I just rewrote what we had figured out on the previous page, and I rewrote basically all our definitions. We got our blob of charge and all our distances. So now what I'm going to do is write out epsilon explicitly. Because remember, on the previous page, we said epsilon is equal to r prime over r squared minus 2 r prime over r cosine of theta. That's how we defined our epsilon. So I'm going to plug all this junk in for epsilon. But before I do that, I'm going to find epsilon squared and epsilon cubed. So, to make things easier, in our definition of epsilon, I'm going to pull out r prime over r. So, we can call our epsilon this instead. And this will be easier when we try to square it. So, now we're going to do epsilon squared. There we found epsilon squared, now we're going to do epsilon cubed. Okay, so there's our epsilon cubed. Now we plug all of this back into our 1 over big R expression. Okay, there we go. We just plugged epsilon in to this thing, and it got a whole lot messier. But I promise it's going to look nice and neat after we do this last step, where we're going to collect all the like powers of r prime over r. So we're going to do that now. And I'm only going to do the first couple like terms. So what I mean is I'm going to collect all the terms that only have r prime over r to the first power, so those are all going to go in one term, and then all the terms with r prime over r squared, they're going to go in another term, and so on and so forth. So I collected all the like powers of r prime over r. I just didn't do all of them. I didn't go past the third power. Now, if you know a lot of mathematics, you might see a trend here. Each term is what's called a Legendre polynomial. So, for instance, this first term here, after the r prime over r, is the first Legendre polynomial. This part right here is the second Legendre polynomial. This part's the third, and if we were to keep writing, it would keep going on like that. So I think that's pretty neat. We weren't really doing any theoretical mathematics, but what we just did was generate we produced a Legendre generating function. So to find the nth order Legendre polynomial, you can use this method where we were Taylor expanding this epsilon term. So, in other words, we can rewrite this 1 over big R as 1 over R times the sum from n equals 0 to infinity of r prime over r to the n times p sub n of cosine theta, where the p sub n is the nth Legendre polynomial. Let's write that. Now that we got that hard part out of the way, we have an expression for our 1 over big R, and we're going to look back at our potential and plug this 1 over big R in for our potential. Okay, so here's everything we've done so far. We've found our 1 over big R term. This is the potential for a point charge. And, well, this is the problem we're focused on, and I don't think I mentioned at the beginning of the video, if we want to find the potential at point P from this blob of charge distribution, well, we're going to have to do calculus like such. Our potential, well, at point P is going to be, we're going to have all its constants out front, 4 pi epsilon naught. And we're going to have to integrate over all space that the blob occupies. And we're going to have a charge distribution. And it's going to be a function of this R prime position. And we're going to divide that by the big R. So the big R is synonymous to this little r in our point charge case. And we're going to have to integrate over all space. So rho here is our charge distribution, or you might want to think of it charge per unit volume, and our r is essentially well, the distance to point P. So, well, in 3 dimensions, the big R is going to be x squared plus y squared plus z squared, the square root of all that. So it's just the distance to point P. So now we can rewrite this because we have this 1 over r up here. So I'm going to plug that in here. So we get the potential at point P equals now we can bring 1 over little r outside of the integral because it does not depend on d tau here. In other words, d tau is just our volume element. So the only dependence we have inside this integral is this r prime part. We can take everything else outside the integral. Now let's say you go look up your Legendre polynomials and you rewrite this. I'm going to do that so we make this a little bit more explicit. I just realized I forgot to put the rows up here. So let's do that. Okay, those should have been written in there. Good job if you got that. Okay. So there's our charge distribution. Now our 0th Legendre polynomial is just 1. So we're going to leave that there. Our second Legendre polynomial is just cosine theta. We found that out basically a couple pages ago. our second order Legendre polynomial is three over 2 cosine squared theta minus 1/2, which we also found a couple pages ago. So this is pretty much the result we were working towards the whole video. The potential due to any charge distribution is going to equal this stuff right here. And the first part is the monopole term, and the second term is the dipole term, third term is the quadrupole term, so on and so forth. So the potential due to just a monopole is the first, well, you have to distribute this, and then it's the first term. So if we were to distribute this little r, you would see that the monopole dependence, well, let's summarize this here as dependence on little r. So for a monopole, it goes as 1 over r. For a dipole, it goes as 1 over r squared. For a quadrupole, goes as 1 over r cubed. Octupole would be 1 over r to the 4th, so on and so forth. So if we're very, very far away, what this is telling us is, we'll say you got 2 point charges, and they're a distance. You got 2 point charges. They're distance d apart. But you're standing way over here off the paper. Well, those 2 point charges are basically just going to look like a monopole because you're so far away from it. Because as r gets bigger and bigger and bigger, the monopole term dominates more and more and more. Because the other ones are pretty much going to be nothing. So I hope that makes sense. That was an explanation on the multipole expansion. You can see from the expansion we get a monopole part and a dipole part and a quadrupole part, so on and so forth. And usually we just think about the monopole and dipole terms. There's some things having to do with nonlinear spectroscopies and so forth that focus on the quadrupole terms. And you're really advanced if you're thinking about the octupole terms. You got really good instrumentation if you're working with those. So I hope that video was helpful, insightful, and I hope you learned something. Thanks for watching, and have a great day.